Hello everyone, my name is Nilesh Kumar Prasad and I will be presenting a topic fluorescence spectroscopy. So let's start. So what is fluorescence? At room temperature, most of the molecules occupy the lowest vibrational level of the ground electronic state, and on absorption of light they are evaluated to produce excited state. Fluorescence is the emission of light by a substance that absorbs light or electromagnetic radiation. It's a form of luminescence. In most of the cases, the emitted light has a longer wavelength and therefore lower energy than the absorbed radiation. So, in the lower diagram, we can see that when the wavelength increases, the energy decreases, and when the energy increases, wavelength decreases. So uh, we have luminescence. Its fluorescence is a form of luminescence. So let's check what is luminescence and the nature of light. A hot body that emits radiation solely because of its high temperature is said to exhibit incandescence, and all the other form of light emission are called luminescence. In luminescence, the system loses energy if the emission is to be continuous. Yes, some of the energy must be supplied from external. When external supply is by a means of absorption of infrared, visible, ultraviolet lights, the light, the emitted light is called photoluminescence, and this is the process that takes place in photofluorometric analysis. So the energy carried out by one quanta is proportional to its frequency of oscillation, that is equal to h mu. Since the amount of energy per Einstein is proportional to the frequency of radiation, it varies enormously over the range of electromagnetic spectrum as shown in the table. So let's check out the table. According to this table, the absorption or the emission radiation involves for X-ray and ultraviolet rays. In X-ray, the transition of inner atomic electron, and in ultraviolet rays, the transition of outer atomic electron. So, in fluorescence, ultraviolet rays are mostly used. So, and what is transition? So, transition when an electron jumps from lower energy level to higher energy level, it's called transition. So let's move to the next. The absorption of the light result in the formation of excited molecule, which can in turn dissipates the energy by decomposition, reaction, or re-emission. In our case, it's re-emission. The efficiency with which this process takes place is called quantum efficiency, and in case of photoluminescence, it can be defined as phi e, that is Einstein emitted or the number of quantum emitted Einstein absorbed by Einstein absorbed or the number of quantum absorbed. And one more thing it's to be noted, it's never a unity. So let's move to the topic, that is our main topic, fluorescence spectroscopy. Fluorescence spectroscopy is a spectroscopic technique in which molecular fluorescence is measured by exciting the sample at an absorption wavelength, and also called the excitation wavelength. Examines the wavelength of the photon emitted by an atom or a molecule during their transition from excited to the lower energy state. The emission of longer wavelength called the emission or the fluorescence wavelength. This shift to longer wavelength is called stock shift. Device that measures fluorescence are called fluorometry or fluoriometry. So in fluorescence spectroscopy, stock shift plays an important role. So let's check it out. In stock shift, what is stock shift? Stock shift is the difference between the position of the band of maximum of the absorption and the emission spectra. The energy of the emission is typically less than that of the absorption. The fluorescence typically occur at lower energy or longer wavelength. So in this diagram we can see that red one is the peak for the absorption, and the dotted blue is the peak for the emission. So this is the Jablonski diagram for fluorescence. Here the here we can see that first the energy is absorbed by the sample, and when the energy is emitted, loss of energy to the environment, and in our case it's in a form of light or invisible range. Here blue peak represent the absorption wave, and red peak represent the wave for emitted. So let's move for the next. Instrumentation. All fluorometric instrumentation contain three basic items: a source, a sample holder, and a detector. Simple and sophisticated filter fluorometry, have a means of analyzing the spectral distribution of light from a sample, and the fluorescence emission spectrum may be by means of either continuously variable interfering filter or a monochromator. In more sophisticated instrument, monochromator are provided for both the selection of excited light and the analysis of the simple emission. So this is the diagram for fluorescence spectroscopy. The emission light first filtered in monochromator, then it passed to the sample. When the sample get excited, it return to the ground state. It emit radiation, and the emitted radiation is again filtered by the secondary monochromator, and after the filtration we get the desired wavelength in the detector, and from detector we get it from in the spectral output. So light source, the first light source commonly employed a source in fluorescence spectroscopy that has a spectral output either as a continuum of energy over a wide range or as a series of discrete lines. An example of the first type of is the tungsten halogen lamp, and of the latter a mercury lamp. It is advantageous to employ a source whose output is continuum, and the most commonly employed type is xenon arc. Here in fluorescence spectroscopy, wavelength selection is also plays an important role. So let's see, the simplest filter fluorometer use fixed filter to isolate both the excited and the emitted wavelength. To isolate one particular wavelength from a source emitted in a line spectrum, a pair of cutoff filter are all that is required. That may be either a glass filter or a solution in curvates. Recently, interference filters having high transition, that is about 40%, and of a narrow range, that is 10 to 15 nanometer of wavelength, have become available, and it is possible to purchase a filter with a maximum transition at a desired wavelength. UV filters of this type, however, are expensive and limited range. However, it is useful to be able to scan the emission from the sample to check the impurity and optimize condition. A convenient method to make use of the continuous interference filter so that the emission spectrum can be recorded at over the visible range of the spectrum. At further refinement would be able to use monochromator to select both the excitation and emission wavelength. Such a fluorescence spectrometer is capable of recording both the excitation and emission spectra, and therefore the mask therefore makes useful full use of the analytical potential of the technique. If monochromator are employed, it should be possible to change the slit width of both the excitation and emission monochromator independently. So let's see detector. A commercial fluorescence instrument use photomultiplier tube as a detector, and a wide variety of the type are available. This material from which the photocathode is made determines the spectral range of the photomultiplier, and generally two tubes are required to cover up the complete UV visible range. The 5S can be used to detect fluorescence out to an approximately 650 nanometer, but if necessary to measure emission of longer wavelength, a special red sensitive S20 photomultiplier should be employed. Readout devices. Readout devices. The output from the detector is amplified and readed readout devices, which may be a meter or digital display. Microprocessor electronic provide output directly compatible with a printer system and computer, eliminating any possible of operator error in transferring data. Sample holder. The majority of the fluorescence S are carried out in a solution, and final measurement being made up upon the sample containing a cuvette or in a flow cell. Cuvette may be carried out a square or a rectangular, and must be constructed of a material that will transmit both the incidence and the emitted light. Square cuvette or a cell will be found to be most precise since the parameter of the path length and the parallelism are easier to maintain during the manufacture. However, round cuvette are suitable for many more routine application and have an advantage of being less expensive. The curvette is placed normal to the incident beam, and the resulting fluorescence is given off equally in all the direction and may be collected from either from the front surface of the cell or at right angle to the beam or in line. So in fluorescence spectroscopy, mostly at right angle, because it prevent the detector to direct interaction of the incoming electromagnetic radiation. So let's check it out, the advantage of fluorescence spectroscopy. It's very sensitive and can be used for quantitation of fluorescent spatial assay and quick to perform analysis. Disadvantage: not useful for identification. Not all compounds are fluorescent, and contamination can quench the fluorescence and hence give false or no result. Application: determination of fluorescent drugs in low doses, formulation in the presence of non-fluorescent excipients. In carrying out the limited test where the impurity is fluorescent, useful of studying the building of drugs to component in the complex formulation, widely used in bioanalysis for measuring a small amount of drugs and for studying drug protein building. Factor interfering with fluorescence intensity, concentration of the solution, transition type in fluorescence, structure, temperature, its solvent, and impurity present in the solvent. So this is all about fluorescence spectroscopy. I hope you will like it. Thank you.